Hi.
Hi, I'm Varun from the Student Council of Aerospace and Geodesy.
Hi, Victor.
Nice to meet you. Can you give a brief introduction of yourself to the viewers?
So basically, I'm part of FSD's navigation group. So our job is to take sensor inputs, process them, give them to the control guys so that they can do their control magic. So the first in the chain, basically.
Do you have any current projects going on?
So we have multiple projects going on, most of them tied currently to unmanned systems, some larger, some smaller, and I would say the main hot topic right now is GNSS denial. So basically we try to come up with alternatives to GNSS. And this might be cameras, this might be LiDARs, this might be radar. You might use the radio link itself, actually.
And how do you get data from these sensors?
It depends. Some stuff you can simulate quite well. For the other stuff, I would say it's a little bit tricky to simulate. Still, things are getting better, but basically what we actually have to do is go outside, because then we get the perspective right. We get, for example, for cameras especially, you get the lighting right, you get all these natural effects that are really hard to simulate.
And do you think we can go outside to take a look at one of these drones that you fly?
Yeah.
All right.
Then let's go outside.
Let's go. So what are we looking at here?
So this is one of our test platforms, one of the smaller ones. So we have an isolated system. So this is just a flight part. This just has to be dependable, nothing fancy here. And then on the bottom, this orange 3D printed part, this is actually the payload we are testing. So this is what we're interested in. This just basically has to do a job.
Can we take a deeper look into the exact systems on this drone?
So what you have here on the bottom is basically a communication power network layer. So you have just power distribution. So this is, you take the raw battery voltage, and then for different systems, we have a power distribution that either gives us 5 volts, 12 volts, or raw battery voltage, depending on what the system actually need. So that's quite modular, so you can plug in whatever you need. Then also usually we have a radio link down there, so you can actually remotely dial into your payload. While you're flying, for example, you have a second person ground station that can dial in and see what's going on in the system. Then you have a second layer, which is a ground truth layer. So that's your reference. If you do testing at the end, what we care about for navigation is we want to see how accurate is our own solution. So for that, what we need is a second solution that might not be 100% accurate, but it gives you a good comparison, basically, what you're at. This is this layer here. And then usually you have the system under test, which is here on the bottom. So this is the actual system that gets evaluated. So this is usually a fully isolated navigation system that just happens to be hanging on the payload. Wow. So this is usually the computer, other sensors, camera, inertial measurement units, and so on and so on and so on.
And I can see that we have 2 Pixel GPS modules.
Yeah, okay. So this one is for the payload.
Okay.
And the second part is for the flight part. So the systems are isolated on purpose. The idea is here on the top, we don't want to do any experiments. And here we can do the experiments. So if we say have a bug in our code, okay, that's not nice because the payload isn't working, but at least we don't have a system that's coming crashing down. So this has to just be dependable, nothing fancy. Here the fancy stuff.
Right. And I see that you also have a router on this side.
Yeah. So the idea is we try to get most of our sensors at this point towards Ethernet. So everything is networked. And basically what this does from you from a system perspective, there's a lot less different interface you have to deal with. So previously you had one RS-232 interface, then you had some discrete synchronization pulses and whatnot. As more and more sensors are actually moving towards Ethernet, everything is over Ethernet, and also if you have to synchronize different measurements, there is a protocol standardized exactly for that, for the time synchronization. So basically, if you go through Ethernet, it's a big hassle in the start, but at the end it makes your final job easier. And that's what we're trying to get to here with this drone.
So what are some things that you usually keep in mind before flight testing? Okay,
so flight testing, at least for us to be efficient, is a lot of planning up front. So you have to think about what do you want to see in your data at the end. So what are we looking for? This depends. You think about, okay, what could be caveats in your sensor? For let's take a camera. There, it's a huge problem with different lighting conditions. So you have to plan, okay, which time of day am I out? Am I looking into the sun? Am I looking away from the sun? In general, is it overcast? Maybe that's for some systems easier, for some systems it's harder. So that's the first part. You basically plan out what do you want to see in the data, and then the second part obviously is doing testing. usually nothing perfectly goes to plan. So you have to have an ability in the field to have someone to look at the data quickly and say, okay, actually we have to redo this test point, or maybe we have to change some test conditions on the spot, on the fly, basically.
All right, then I guess it's time for some flight testing now to see this thing fly. All right, let's do it. What sensors do you usually test on this page?
So what we do is a radio link, what's quite interesting actually, because from the time of flight between two radio stations, you can also use that for positioning. Then obviously GNSS. Yeah, GNSS right now is a little bit difficult because it's really easy to jam or even just involuntary interference. So it's quite difficult to use that sometimes, or at least right now, for flight. And then what we also can put down there is LiDARs, cameras, or even radars.
And why test it on a drone? Why not on a table somewhere on the ground?
The thing is, what we care about is motion. And even if you say you put a sensor on a car and drive it around, you never will get the accelerations or the movement or type of movements that you will actually get by flying. Second part is, especially for those smaller vehicles or basically anything that hovers, so as a big rotor providing the lift, vibration is a big problem. And this is one of the best ways to actually replicate it, just go out, fly it.
So what's the primary sensor?
The primary sensor of most drones is actually an IMU.
Can you briefly explain what an IMU is?
So IMU, inertial measuring unit, is actually two sensors combined in one package. So you have once the accelerometers, which just roughly speaking measure acceleration. And then you have the second part, the gyroscopes, which measure your angular rate. And if you combine both, you can do cool stuff like integrate those up to get position, velocity, or your attitude. And obviously also the controls guys like it if you give them accelerations and angular rates, so you can do the controls.
Is there anywhere that you usually test these IMUs before for using on these drones?
So there are multiple tests you can do. Some of them are just static.
Okay.
Some of them apply that you, or basically require that you apply a very defined signal. And for that, we actually have a specialized test equipment, which is quite high grade. So we can really see what we get from the manufacturer, if it's like true to the data sheet of its marketing.
Do you think we can take a look at the setup?
Yeah, sure. So it's actually called a rate table. What I suggest, we just go inside now and I'll show you around. All right, so this is our rate table. And what we use it for, as I said before, is IMU testing. As you can see, it's quite a beast, but it has to be. I think if you want, I can explain later why. Yeah, it's basically you put the IMU on there, and then you can either rotate it to different attitudes, positions, or you can spin it around. So it's the two different sensors, the accelerometer, you stimulate using gravity in different orientations, or for the gyroscope, you just stimulate them yourself by just spinning them using the table. So as you can see, you have multiple axes you can use, which allows you to reach the different test points. All right. So this is where you control it. So this is the main electrical cabinet with the real-time PC and a GUI PC, so two different systems. And then you have a second computer running MATLAB on it. So you can either control directly through here, or you can write a MATLAB program that then sends over the command to this one and also controls the table.
Thank you so much for showing us the rate table and the drone flying around. But before we end it off, what is one advice you'd give to the TUM aerospace students?
Do private projects, really. Just don't sit just in the lectures and take the stuff in. Actually do private projects, because then you're forced to apply it. And there you run into 1,000 problems we don't tell you about in lectures. But at the end, that's what makes you a good engineer, really.
Very cool. All right, thank you very much for your time.